Hey everybody, it's Dr. Wood, and today we're going to continue on talking about our biostatistics and talking about the rest of statistics. Basically everything else you haven't covered is going to be here, so buckle up. It's probably going to be an 8-10 hour lecture. Just kidding. Just talking about a couple other things that are sort of common things you might run into in terms of the medical literature. So here are my objectives. We'll cover these as we go forward. And so the first thing I want to talk about is something called the analysis of variance. And if you remember our talk on students' t-tests and things like that, this is going to be important to understanding the analysis of variance, or ANOVA. So an ANOVA, or analysis of variance, is going to be basically a collection of statistical models in which we're going to be looking for variances in a particular variable, some kind of outcome, as it is being applied to different sources of variation, right? And so basically what this means is that we're looking to use ANOVA as a statistical test to see whether or not the means between several groups are all equal or not. And so this is sort of like using a t-test when you have more than two groups. T-tests are really good just for comparing one group to another to see if there's any statistically significant difference between their means, whatever outcome you're looking at. Here, by using ANOVA, we can look at multiple groups at the same time. So we can use 3, 4, 5 different groups if we want, in order to see, is there a difference amongst one of those groups. The problem is, if I keep using a 2-sample t-test over and over again, I'm going to keep increasing my chance for causing a type 1 error. And so by using ANOVA, this is a much better way to make sure you don't run into that problem. You're less likely to make a type 1 error and say there is a difference, and you reject your null hypothesis when you probably shouldn't have. A one-way ANOVA is going to be comparing those means of 3 or more groups, as we said, and we're assuming this is coming from a Gaussian population. There's other ways to do this when you have a non-Gaussian population, but let's focus on this first. And we're looking at a study from 1993, and they were interested in hormonal changes in female runners. And basically they're looking at levels of luteinizing hormone, or LH, in non-runners and recreational runners, and then elite runners. And so what they're trying to figure out is there a difference in luteinizing hormone between these three groups here? And if so, follow-up questions are going to be, well, where is the difference at? And so they looked at the distribution of hormone levels. It appeared to be log normal, so then they changed that to a logarithm, so they did the analysis a little bit easier here. And then while most studies don't publish the raw data, they did give you a summary. And so that's what we're going to be looking at here. And so you're going to find that obviously luteinizing hormones don't predict if someone's a runner or not, but we can see whether or not there's a difference in the expression of luteinizing hormone based on whether the person is a runner or not, right? And so let's look at the data here. So we can see here the three groups: non-runners, recreational, and elite runners. Again, the study would have to define what that means. Whether elite runners means they've run a marathon before, or how many miles they run a week, whatever the case may be, versus recreational versus non-runners. You can see here they have the log of the luteinizing hormone, standard deviation, standard error of the mean, and then the n that they had here. And you notice here the elite runners are less. The n is much smaller here, which makes sense because it's probably harder to be an elite runner than just recreational, or it's actually very easy to be a non-runner. I've been a non-runner practically my entire life. However, looking at this, you can see they put the mean and the standard deviations, kind of comparing the three groups together. Just looking at this, it would appear to see like the non-runners have a higher luteinizing hormone than the elite or the recreational. However, it's really hard to tell a difference just by looking at the data itself, right? So this is where we have to run these tests to see, is there a difference amongst these groups? Now, if it was just, say, elite versus recreational, I could just run a t-test between these two, and that's no problem. Since we have more than two groups, this is where the ANOVA is going to come into play. So, as I mentioned, an unpaired t-test would have to be run between non-runners and recreational runners, recreational and elite, and then non-runners to elite runners. Again, as I mentioned, with multiple comparisons, you're increasing your chances of finding a true difference, or trying a difference just by chance alone. And so because of that, you're increasing your chance for a type 1 error. Now, when you're looking at these three groups, if the null hypothesis was true and you kept making these comparisons, there's a 5% chance that each time you run a t-test, you'd get a significant p-value. And again, that's not great. We're going to make sure we try to run as few comparisons as possible. Or if we're going to run multiple comparisons, you have to correct for that, right? Remember those Bonferroni corrections we talked about before? But this is a better way, right? We can just run an ANOVA here and basically say, well, just for this one comparison, we still have that 5% chance of finding a type 1 error, but we can see whether or not we think that there's a group amongst any of these, or a difference between any of these groups here, or are they all basically the same. So as I mentioned, the one-way ANOVA compares all the groups at one time, and when you end up calculating a one-way ANOVA, the p-value ended up being 0.0039, meaning that the differences that you found amongst the three groups and their mean LH levels is very unlikely just to be due to chance alone. It's less than a 1% chance. It's 0.039% chance. This is just due to random variation by itself. And so here we can reject the null hypothesis that says there's no difference amongst the groups and that there must be a difference amongst at least one of the comparisons of groups. We just don't know which one it is yet. So again, this is based on the same assumptions as an unpaired t-test. So the sample should be randomly selected. The observations with each one are obtained independently, so you don't have the same person being measured twice or twins or anything like that. And that it should be coming from a Gaussian distribution. Hopefully the standard deviation of the populations are identical, but should be fairly close. Now you could also do what they call a repeated measures ANOVA, but this is basically the difference between an unpaired and a paired t-test. Repeated measures ANOVA is going to be used if you have, say, samples that come from the same groups, or if you were maybe running the same laboratory experiment several times and they're somewhat related to one another. So because of that, that's where you get a repeated measures ANOVA. Just a regular standard ANOVA, one-way ANOVA is going to be used for independent samples. Now, if you wanted to look at not just what their running categorization was, but you also wanted to look at another independent variable, this is where you could start to get into much more complicated ANOVAs, things like a two-way ANOVA, where you could actually compare and categorize the patients not only based off if they're runners or not, but also their age groups, right? And again, this gets more and more complicated. Typically, one-way ANOVAs are going to be the most common ones you're going to be running into. If you're to run a two-way ANOVA, basically it's testing three different null hypotheses and getting three different p-values here. And basically, one, they're looking for the interaction, where there's no interaction between the two different factors here. So they're looking to see, okay, well, you know, there's no interaction between LH levels based off of exercise and age groups, right? So exercise and age group have no interaction on one another. And then the first factor they're looking at is the null hypothesis that exercise has no effect on LH levels, and then you look at the secondary factor saying, does age have any effect on the LH levels? And so getting three different p-values here, you can see that, okay, well, is there any interaction between the two independent variables? And then you look at each one of those individually. So once we get an ANOVA, a one-way ANOVA, and it comes back with a low p-value, we can reject the null hypothesis that says there's no difference between the different groups. And after this, we have to kind of figure out, well, where does that difference lie? Where, you know, between which groups is there a statistically significant difference? And this is where the repeated, this is where multiple comparisons after an ANOVA come into play here. As I mentioned, one-way ANOVAs only compute one single p-value that says there's a difference somewhere, but it doesn't tell us where. And so by using multiple comparison tests and making sure we're accounting for the fact that we're running multiple comparisons, we can then dig deeper into the data to determine where the actual statistically significant differences lie. So this is where we can run into multiple comparison tests for the example data here. And again, we have the LH levels for three groups of women. The one-way ANOVA gave us a very small p-value, saying that we can reject the null hypothesis that says that there's no difference between the groups. And then now what we can do is look at a family of comparisons where overall significance level is going to be defined as 0.05. This is kind of like using the Bonferroni correction before, where you're looking for a family-wise error rate rather than looking for a comparison-wise error rate. And remember, this helps us to reduce the number of type 1 errors we make, but we may be more likely to make a type 2 error. So in order to compare each of those means together without causing a multiple comparisons issue here and causing a type 1 error is use what we call a Tukey's test. And so this is basically going to be giving us a better idea of this, the comparisons between the groups by using this kind of family-wise error rate rather than using a per comparison error rate, and it prevents us from making that type 1 error as we mentioned here. And so looking at this, we're going to find that each of the groups was compared together. So we have recreational versus elite, non-runners versus elite, and so on and so forth. And you can see here that when you end up running these sort of family-wise comparisons rates, that you see that the confidence intervals tend to get bigger, right? Because we're giving ourselves more wiggle room, and it's harder to achieve that significance, and thus you're less likely to make that type 1 error here. But if you're looking here, looking at the difference, right, the mean difference in the log, if the 95% confidence interval crosses 0, because if there's no difference, then 10 minus 10 is 0, then you would see that it would not be a statistically significant difference in the means. So looking at recreational versus elite, notice here how it crosses 0. So we can say here there's no statistically significant difference in the mean LH expression between these two groups. With non-runners versus elite, it gets pretty close, but it does not quite achieve that level of significance. And then looking at non-runners versus recreational, notice here it does not include 0, so this would be the one statistically significant difference in means out of the data that we have, even though the other two could have maybe shown a difference, they ultimately did not. So the ANOVA basically said, hey, there's a difference here somewhere in these groups, we just don't know where, and then we do the Tukey's test afterwards to determine, okay, actually it was between the non-runners and the recreational runners. Now, is it possible that there could have been multiples of these that were significant? Sure, and this test would be able to tell us that as well. And here's just a table showing you the Tukey's multiple comparisons test here, looking at the differences between the means and then the confidence intervals here. Notice the non-runners versus recreational were the only one that did not cross 0, because these end up going into the negative, or they do cross 0, you end up seeing that these are not going to be statistically significant. Now remember, when you did that Tukey's test, because you're running these multiple comparisons, that 5% significance level gets applied to the entire set or the entire family. And again, that makes it more difficult for each one of those to achieve significance, because you find that the confidence intervals get wider, but because of that, you're less likely to make one of those type 1 errors. Okay. So overall, if there's no difference between any of the 3 groups or any of the 3 comparisons you're making, each one of those, added all together, would have a 5% chance of finding a difference when none truly existed. As I mentioned, with more groups, the confidence intervals become wider, because imagine if you only have 3 groups, you're just divvying up that 5% over 3, right? Versus if I were to have, say, 5 groups, you end up having 10 different comparisons you'd be making there. And so because of that, you need to divvy up that significance level over, or that 5% over more comparisons. And so it makes it harder and harder and harder to achieve significance. And that's evidenced by the fact that the confidence intervals get wider, which means it's more likely to cross 0, right? Or if you're doing like a ratio, it's more likely to cross 1. So that's important to note there. And again, multiple comparison tests use the data from all the groups, even if you're only just comparing 2 together, right? Because again, the one-way ANOVA is based off the assumption that all the data are sampled from a population with the same standard deviation, even if the means do end up differing there. And so that's just one of those assumptions that we use for the multiple comparisons to give us a little bit more power. Again, as I mentioned, when you see the number of groups increase, you see that the number of pairwise comparisons goes up pretty exponentially, to the point where if you had 10 different groups you're comparing, and if you ran in an ANOVA and you did find a difference somewhere in those groups, you'd have to run 45 different pairwise comparisons to find out where the significance actually lied. And so to prevent that type 1 error, you'd have to take that 5% error rate and then divvy that up over 45 different comparisons. And so because of that, it would be very difficult to show significance. However, if something did show significance, you know that really is truly different between the 2 comparisons. So the next thing I want to talk about here is going to be what we call non-parametric methods. So basically, a non-parametric test is removing the assumption that you're working with a normally distributed set of data, right? You're basically saying, well, I'm not really sure if my data is Gaussian distribution. I'm not really sure, or the test for normality perhaps failed and shows me that I'm working with a non-normally distributed set of data here. This is where you can use the non-parametric test as your backup. Note when we talked about unpaired t-tests and ANOVA, it was always working under the assumption that it had a Gaussian distribution. Thus, they call those parametric tests, because they can be defined by their parameters, right? So we call them parametric tests. However, with non-parametric tests, we're not making any assumptions about the distribution of the populations. Instead of looking at the actual values, because remember, outliers tend to be a problem when dealing with means and things like that. With non-parametric tests, we're taking that out and we're just ranking everything up in order from lowest to highest. And so by doing that, you are comparing the ranks, not necessarily the values. And so the effect of outliers is going to be greatly diminished, and thus you're able to use this for non-normally distributed data. It makes it more difficult to show significance. We consider these to be a little bit more conservative, but it also means you're less likely to make one of those type 1 errors. So they're considered to be a little bit more robust. So what if we wanted to compare 2 unpaired groups together? This is where we come up with the Mann-Whitney test. Now, some of these can be a little difficult to memorize what they're used for, mainly because they're named after the statisticians who developed them. And so in this case here, there's something you're just going to have to remember with kind of repeated viewing here. But a Mann-Whitney U-test is basically a non-parametric test to compare 2 unpaired groups and compute a p-value. Kind of think about this as being the non-parametric comparison to the t-test. And again, basically what you end up doing is you just rank up all the values together without really looking at the values themselves. And then you sum the ranks of each group, you calculate a mean rank from each group, and then you compare those 2 together, right? Again, the point of this is that it's removing the effects of outliers or if you know you're dealing with a data set that is non-Gaussian, or if you're not sure you didn't run the test for normality, this is always a safe backup to use because it is more robust, more difficult to show significance, but when you do show it, you're quite sure that it is actually a true difference between the groups there. So let's look at this experiment where they're looking at the relaxation of the animal bladders together and comparing the old versus the young animals. And notice here that each one of these values from smallest to largest ends up getting a rank. And so you can kind of see here how the old ones have the lowest values get the first rank as they go up. Notice here they're kind of interspersed. And basically by adding all these ranks up together and dividing it out, you get a mean rank between the young and the old, and then you compare those mean ranks together, and that will give you a p-value. Basically what it just means is that you have an outlier that's up here. It doesn't really skew your data that much because it doesn't really matter what the value is, it just matters what rank it ended up being. Another way that we can do this would be to compare two paired groups. This is where we have a Wilcoxon matched pairs signed rank test. And again, some of these names are a little bit of a mouthful here. But if you have two paired groups, so just like we have a paired t-test, this is where the Wilcoxon rank sum test comes into play. I'm not going to have you actually calculate it through, but the general process is going to be the same, where you're basically assigning ranks to all the values and then comparing the mean ranks between the two groups here. Okay, and again, the assumptions are gone that you have to have a Gaussian distribution. The only assumption here is that the two sets of data are actually paired, right? So they're not independent, they are dependent. You could have pre and post challenges, you can have siblings, etc. That's totally fine here. So let's look at the problems. Let's say we were to accidentally use a non-parametric test on a Gaussian population and vice versa, and to see what kind of problems we run into, and then looking at the effects of small versus large sample sizes here. So when we're looking at, say for instance, a Gaussian population, and we just happen to know this is true, and we have a non-parametric test being run here. The problem with the non-parametric tests is they typically have less power to show differences, especially in small sample sizes. We consider these to be more robust, and so it's more difficult to achieve significance, but when you do, again, you can be more sure that there is a true difference. So this can be really tough. However, the large sample size is probably not going to make really that big of a difference, right, overall. With a non-Gaussian population, normally you'd use non-parametric tests, but instead if you were to use a parametric test, this can be really misleading. Because they're not very robust, they tend to be more likely to find a type 1 error. So again, if you use non-parametric tests in a Gaussian population, you're more likely to see a type 2 error. With a parametric test in a non-Gaussian population, you're more likely to see a type 1 error. Again, with the large sample size, probably doesn't make a difference, but in a lot of these medical trials, you tend to find that data sets may be fairly small. And again, how can you tell the difference? Well, using normality testing can really help you out with that, especially to determining which type of test you should be using in the first place. So now we've discussed the issue of parametric versus non-parametric tests. Let's talk a little bit about sample size. Now, a lot of experiments tend to be run with far too few people in it. It's because it can be really difficult to get people into your study. Either it's a rare disease state, or you don't have much money to recruit people, things like that. And so very frequently you find most studies tend to be underpowered, meaning that if they don't find any differences, then it could just be because they didn't have enough people to really show that difference. They made a type 2 error. And even if treatment substantially changed the outcome, there's just a very small chance we'd be able to find it because there's just not enough people to show that. So there's a couple different ways you can get your sample size figured out. There's an ad hoc, which is not necessarily recommended, mainly because you're just collecting data and you're analyzing it as it comes along. And then as you get more data, then you kind of reanalyze it. And so you tend to find that it's not super valid to run p-values and confidence intervals with this method here. More often than not, though, what we can do is to conventionally choose a sample size beforehand. And to do that, we do what we call a power calculation, where we determine how many people we need to recruit into a study in order to show a given difference. Okay, that way, if we run that study and we don't find a difference, we can be relatively assured that there's no difference there. Versus if we do find something, we say, well, the data set was definitely powered to find that difference, and we found it, right? Sometimes you have what they call adaptive trials, where the interim analyses will be kind of performed while it's still running to decide how you need to change the course. Sometimes they'll shorten it, where they say, hey, we have enough data to show the difference here because it's so obvious. Sometimes you need to lengthen it out and recruit more people. It just depends. But the conventional way at least should be addressed in the paper to show that, hey, we at least came up with a power calculation. We think this is how many people we need to show our differences. And again, the width of the confidence interval depends on the sample size. And if you have a larger sample size, narrow confidence intervals are going to be obtained there. And again, it's going to be useful because the wider that confidence interval gets, the less likely are to show a true difference when you're actually making those comparisons. So that's it for this section. If you have any questions, let me know, and I'll talk to you next time. Thanks a lot. Bye.